Welcome to Study Loop.
Here we need to find the change of volume due to heating, due to temperature increase of a liquid. Liquids also expand, like gases, but they expand in much lesser magnitudes. And the law which dictates the expansion of the liquid under some temperature change is a little bit different than for the case of gases. So first we will express this law. So the change of volume equals beta times initial volume times delta T, the change in temperature. So beta here is called the thermal coefficient of the volume. And for the given liquid, which is methanol, we need to find it from the table 17.2 in the textbook, so the value for this coefficient. When we find this value, we can substitute the rest of the given values and directly calculate. This will be equal to 1.5 times 10 to the minus third. This is going to be 1 over Kelvin times 1.2 times 10 to the negative 2 meters, and this is the length, so it will be cubed for the volume. And here we have the difference of the temperatures. When we place these values into a calculator and evaluate, we obtain that the change in volume is 4.32 times 10 to the negative 4 power meters cubed. So this was for the part A of the problem, which was the most important part, since we will use this value through the rest of the problem. For the part B, we need to find the work done. So the work done is evaluated in a very similar manner like with gases. It is work done is equal to constant pressure times the change of volume. With liquids, we will always approximate the pressure to be at atmospheric level or some other level, but it is constant. So in this case, we can substitute that the pressure is equal to force over area, since we're given force and we're given areas. So in substitution, this is equal to 3 times 10 to the 4th newtons over the area, which is 0.02 meters squared, and this is going to be times 4.32 times 10 to the minus 4th meters cubed. When we place these values into a calculator, we obtain that the work done is equal to 648 joules. So we have completed the part B of this problem. For the part C of this problem, we need to find the amount of heat that is being added to the methanol liquid to increase the temperature and expand the volume. Now, we will always, this is done in a very similar way like with gases, except the formula is slightly different. So see, Q equals mass, not number of moles, mass times heat capacity under constant pressure and times the change in temperature. So it is very similar but not exactly equal like with the gases. Also notice that in this problem we need to substitute mass with density of the methanol, and actually this is the density of the cube that is being added into the methanol so that metal expands. So we will say this is the density of the cube, see like little c, and the volume of that cube. So You can say that rho C V0 times Cp times delta T. And we can directly substitute all of these values. So this will be 791 kilograms per meters cubed times 1.2 times 10 to the minus second power, and this is on the third. This is supposed to be on the cube, since this is for the volume V0. And next we should, this is going to be in kilograms, of course, and then we should now add the constant, which is 2510 joules per kilogram Kelvin, not per mole Kelvin. So it's per kilogram Kelvin, and this is going to be then, this is 30 kelvins of the temperature difference. All of this will be in joules, but we will, when we evaluate these numbers using a calculator, we obtain that Q equals, and we will express this in kilojoules, 715 kilojoules. This is for the part C of the problem. Now for the part D of the problem, we will use the first law of thermodynamics, because this law works for every phase of the matter, gas, liquid, or solid state, it doesn't matter. So the change in internal energy will be equal to the heat added minus the work done. So since we know the heat added and we know the work done, we can just substitute it into and say that is equal to 715 kilojoules minus 648 times 10 to negative third power, also kilojoules. So this will basically be just joules, and we see that this equals, when we subtract these values, we see delta U equals 714.35, which is approximately equal to 714.5 kilojoules, also kilojoules here. And this is for the part D, where we should see that the Q is much greater than W, so delta U approximately equal to Q. Or all of the heat that is placed into the liquid is going to increase its internal energy and no work done on the surroundings. That's why we use gases for expansions, like in motor engines, instead of liquids. And for the part E, we need to exactly state this, that the difference is not substantial, and we already concluded that the heat is much larger than the work done. So the specific heat capacity when it comes to liquid materials, and also when it comes to solid materials, is usually evaluated at a constant atmospheric pressure, and the change in volume is really small, so we can consider that the volume is constant, and we can always use Cp, or when we calculate something, we can always use Cp, or the heat capacity under constant pressure. So the whole thermodynamic process would not be very inflicted by the Cp or the Cv value. We can use Cp always, and it doesn't really matter which of it we use. So the difference is not great or substantial. This is the answer for the part D of the problem, summarized. And now we have completed the problem. I hope you find this helpful and I hope to see you in another lesson. Bye.